You know, we're good.
We're good. All right. So people are filtering, so I think we can get started with our usual soft start with a bit of chit chat. And so where we are in the semester, we've been talking about a lot of models and a lot of ideas and algorithms and stuff. And I think we're at a good place to start just looking at some of these questions more broadly rather than thinking about, like last week we talked about, how do we debug our objective? We start and we see if it sticks in the same place, those sorts of problems. These are important problems, right? When you are trying to debug a model, if the model is wrong, if the model doesn't work, that's a big deal. But there's a lot of other problems, a lot of other things to think about. The ethics lecture pointed out some of these things. And so the example that I wanted to talk about today, because it is wrong or it has problems in multiple educational ways, is this example where a group of folks tried to take images of people's faces and basically predict straight or gay from those faces. Now you can already think that this has problematic implications. But I want to start, before we get to the problematic implications broadly, I want to start out with just an image of the mean images. And for those of you who are working on your PCA examples, and we just did some k-means, you've been looking at mean images, right, of numbers. So here is an example of mean images that come out of this system. There we go. Let me scroll it down just a little bit. So here are these composite faces. These are coming off of a dating website where they're trying to make predictions. So one thing we notice here is that kind of obvious is just that there's cultural markers, what one could consider cultural markers separating the types of faces. So this system believes that if you wear more makeup, if you're a female and you wear more makeup, you're more likely to be straight. So this is already suggesting that this algorithm is right for if it's getting these predictions right, it's getting them right for the wrong reasons, right? It's picking up how people present themselves on a dating website. Mm. Yeah. Anything else, David, that you wanted to comment just on these like mean images? And then
well, this whole study, I think it's hard for me to think through as to why they were doing the study and, and the implications of the study. I mean, I agree. It's interesting to look at the mean images, and I think you're right to notice the things that the machine learning algorithm is beginning to identify. But I think with a study like this, let's try to unpack the ethics and the morals around, is it valid science? Is it useful to society? It's hard to think through.
Why is this useful to society?
As a white gay man, I remember being, on one hand, shocked, like, really? We can use machine learning algorithms to do this. My next thought was, well, how can that possibly work? And then I remember doing some digging at the time and trying to understand what was behind the results, because it just doesn't seem to conform with things that I would believe to be true. Mm-hmm. And I know there were lots of studies that followed on from what the researchers did.
Right. And found that there weren't really any signals that were legitimate.
And generated confusion, I think. Yeah. Was it because the backgrounds were different? Was it because, like you said, the different people were using makeup in different ways, etc.? But for me, I just keep falling back on, this is an example of concerns around misuse of facial analysis. I mean, we're fortunate to be living in a society where we're free to love the people we want to live, to believe the things that we believe in and we hold true. But there are still people living around the world who don't have those freedoms. And What about false positives? What about false negatives? You know, you can imagine false positives could be particularly problematic here in some societies.
Exactly. I mean, we're kind of in a bubble, even in Cambridge, compared to the
The
rest of
People's
the United
Republic
States.
of Cambridge.
Yes. And there's many parts of the world where this could cause a lot of trouble for people, whether it's a false positive or not, right?
Right.
Yeah, this is not something that people may want known about themselves, because of the way that their society is structured.
Right. But I think also if we get to the data, I think it raises questions about the science. You know, what was the methodology by which they went from the 75,000 dating profiles through the hundreds of thousands of images down to the 35,000 images that they then used in the study? Were the researchers injecting their own biases, their own perceptions into the way they curated their data? That's just one example of how bias can come into the pipeline.
Yeah. And this isn't the only study on faces that's like highly questionable. There's other studies. That one came out around a similar time, a Chinese study predicting criminality based on facial photos and all of these sorts of things. And I think we really like it's so important when you're building a system to think about what it like, whether it's plausible, first of all, but also what's the purpose, right? What is it? And what are, as you're saying, like, what's the false positive implication? What's the false negative implication of anything that's built out there? Because once it's publicized, other people may try to copy it, right? Be like, oh, this is a thing, right? I'm gonna make it. And training machine learning algorithms is so easy these days, that it's widely available. Cool. All right, so that hopefully gives people some food for thought, especially as we're reaching the end of the semester. Folks some of you are going to be graduating, going out into the real world, keeping in mind, you know, what we need to be thinking about as we go out and we put these algorithms out there into practice. Don't make these mistakes, basically. All right, so let us skip or move ahead now to our main technical topic. All right, so here we are. So where are we in the semester, right? So as I said, we're getting close to the end of the semester. We have basically gone through this cube of supervised, unsupervised, discrete Z, discrete Y, continuous Z, continuous Y, probabilistic, non-probabilistic. So we've gone through a bunch of stuff here. And most of these models were relatively simple. So what we ended up doing is that we took some time in the first half of the semester to talk about model selection and model classes, objectives. And now we're going to, in some ways, continue the conversation about extensions or going beyond this cube. And we're going to talk about structured models for the next couple of lectures. And then the last set of lectures are going to focus on decision-making or reinforcement learning. In terms of just a couple of notes in terms of logistics, homework 5 is due this Friday. There's been a bunch of clarifications, especially around the PCA question. So one thing just want to emphasize there, PCA, as we derived, is based off of L2 error. But as long as you're doing an apples to apples comparison of errors in your homework assignment, any choice of error metric is, or L1, L2, L2 squared, averaged, sum, all of these are fine, as long as, again, you're making an apples to apples comparison between what does PCA do and what does something like clustering do. In terms of other notes, practicals are out. And as we said, this week, you may be busy doing homework 5, and that's okay. But there are 2 important things that we would like you to do. First of all, determining your teams is due on Friday, and there's a post to help you find teammates if you don't have teammates already. And also, we highly encourage you to just at least take a look at the sample code that comes with the practical and just see if you can load the data, right? This very small thing that, and most of the practical should be very straightforward. You can do like the basic part of the practical. You can do with using it, because you're allowed to use any libraries you want. You can use sklearn to do various things. So we're hoping, fingers crossed, as long as you can kind of load the data into the environment, then the rest of it should be, you know, relatively straightforward and smooth sailing. So just check that out, make sure that there's no drama there. Again, staff has worked hard to make sure that there isn't. There's also some little videos that Nari has made to help with this initial process if you have any questions or issues or stuff like this. Great. So that is just housekeeping and models with structure. Here we come. All right. So today we're going to be talking about a topic called graphical models. And hopefully it's going to be a bit of a break from things that we've been doing so far, because there's going to be relatively little math and mostly pictures, because graphical models are pictures. And we've been seeing some of these pictures all throughout the semester. What I want to do today is to formalize some of those pictures that we've been seeing. So early in the semester, when we were doing supervised learning, we would draw pictures like this. We would draw pictures like the Y generates the X. This was the generative classifier. And then we also drew pictures like this, where X creates Y, and that was our model for the discriminative classifier. And what these pictures were trying to describe were the story, right, of how the data come to be. So in some sense, they're both generative models, but they have these different names. But the idea here is that there's some hidden label Y, and then you choose that hidden label Y, and you use that to generate the X's. So it's kind of the natural factorization of P of X, Y here should be something like P of Y, P of X given Y. Whereas the natural factorization kind of implied by this model is that P of X, Y is equal to P of X, P of Y given X, right? And so graphical models in this way like encode independencies and code kind of natural ways to factorize. And we're going to make that a bit more formal as we go through today. So this was just one example. More recently, we've seen some more graphical models. And here I'm just pointing out things that we've seen, and we can put them into the same picture type framework. So we saw mixture models. And now I'm going to make our graphical model pictures a little bit more sophisticated. So in our mixture models, our idea was that there were some hidden Z's that were generating the X's. And now I'm going to introduce a bit more notation. So this is called plate notation. So when I put a box around this part, I mean that it's going to be repeated. So for every element in the data set, there's some Z, and it's producing some X, right? So how are those Z's being produced? Well, there's some probabilities pi that choose the category, right? Which is the component that you're going to be selecting from. And those are common to all the data points. So I'm drawing it outside. And then there's also some mixture parameters. There's some mu's and there's some sigmas for the Gaussian mixture model. And there's a bunch of these, right? There's K of these, actually. Let me do this. And actually, here's another opportunity to use a plate. So there's K of these. And the mu's and the sig combine, the Z's, the Z for this particular data point combined with the relevant mu and the sigma produce the X. So this is the idea with the plate notation, and also this idea of here are globals. We've been talking a lot about this idea of globals and this idea of the locals over here. And today we're well, maybe not quite today. Today in next class, we're going to talk about these more general notions of how knowing the structure of a model can help with different types of optimization and inference. Another model that we looked at was topic models. And in topic models, we had some Dirichlet parameters alpha, and they produced these document specific parameters pi in terms of how, what are the proportions of the topic inside the document. And then these topic, remember we introduced that notion of Z. So for every single word, what topic did that word come from? So actually now I'm going to need another little plate over here for the length of the document. And Z produces the word. I didn't need that thing to be quite so big. And then we can get counts of words in the document. That was our X out here. And then the last bit that I need is the theta. There were K topics theta over here that helped predict the word. So these sorts of pictures, you might be wondering, like, what is the point? These look very nice, but what do they do? So again, they're going to be really valuable because they tell us the structure of the data. So these are examples of a general class of models called Bayesian networks. And they're useful for encoding. They help encode the structure of the data, including what we're gonna see, independence relationships. And that's really useful. So these independencies are useful. And we'll see how for two major things. First of all, they're useful for inference. These kind of block coordinate ascent type schemes that we've been looking at so far in class. Actually, let me scroll up so we can see a bit of that. So over here, one thing we can see from the, and I'm going to say this kind of informally now, we'll make it more formal later, is that if I knew the Z, right? So if I'm here, if I know the Z, and just visually from this graph, I've separated pi and mu and sigma, right? So mu and sigma are on one side of Z and pi is on the other side. So if I'm trying to do some inference about pi and mu and sigma, these globals, remember when we did the mixture models and the topic models, once we had the hiddens, things kind of separated out and we were able to solve for means separately from being able to solve for the relative popularity of the different components or the topics. And this is no coincidence. It comes from the fact that if you have the Z known in this graph, then it breaks the graph into these different components that are independent of each other. So this can give you ideas for inference, or what are good ways to do inference. And also we can learn smaller models in the sense that everything here isn't connected to everything else. So these distributions can be more specific, more small, and we'll make that precise as well. But one thing I also want to emphasize here is that we could have changed these from being Gaussian to some other distribution, right? Like a T distribution, a gamma distribution, a Poisson distribution. And the insight that knowing the Z is going to help split up the learning problem into these two important components would not go away, right? So looking at the structure of the model, looking at a Bayesian network can really help us understand ideas about things for inference and such without worrying about the specific parameterization. It stays true across different choices of parameterization. Right. So these are things that might be useful for. Specifically, we're going to be looking at, so today, we're going to focus on a specific kind of Bayesian network, which is called a directed acyclic graph, or DAG for short. And the idea behind a DAG is that we will have a directed graph. Let me just draw some nodes now connected to each other. And so directed means that these edges have arrows associated with them. And acyclic means that there are no cycles in this graph, that there's no, if this arrow was pointing in the other direction, that would be like a cycle here from A, D, C back again. But here, all the cycles point coming outward from somewhere, or several somewheres perhaps. And so there's no loops in the graph. And this sort of graph, the interpretation is that we can simplify okay. I simplified my spelling. Okay. We can simplify the joint probability in a specific way. So if I have the probability of A, B, C, D, and E, and I want to just factor that probability, well, I can always factor that probability just based on rules of probability, right? So I can say this is probability of A, it's probability of B given A, it's the probability of C given B and A, probability of D given A, B, C, probability of E given, running out of space here, but all the other variables, right? That is always true. It is always true that I can take a joint and I can factorize it with conditionals. But what this graph is saying is that I can simplify this in specific ways. So I can make this probability of A. So A doesn't have any parents. Probability of B depends on A, yes. Okay, so I still need to have this guy over here. But when I get to probability of C, oh, oops, I went in the wrong order. I'm just going to change this graph a little bit. Okay, let's make this C, make this D. So when I have the probability of C given B and A, then I know that actually this can be written as probability of C given A, that B doesn't affect C out here, right? That given A, B and C are going to be independent of each other. And again, we're going to get to the specific rules of this in just a moment. This is the way you can read it off the graph itself. And then I get to D. And well, D depends on C and A. It doesn't depend on B. And finally, when I get to E, I can write that as probability of E given D. And the nice thing about this is that when I need to encode these distributions, I can encode now the probability of E given D. That is going to have less parameters in it than the probability of E given, if I was doing some learning, right? Like I needed to learn a probability distribution, a probability table. And I was like, oh, like if I need to learn the probability of E, I need to learn that probability of E for every A, B, and C and D. That would be a lot of things I have to consider. But now I'm saying, no, I only have to consider values of D. So is a dependence only established by a direct arrow connection? So we're going to make this more formal, and we're going to talk, actually, I'm going to go, give me just like a couple minutes, and we'll answer this question in a little more detail. Okay, so let's talk about this dependence in more detail. with an example. So this idea of local independence. So I'm going to give an example where we're going to go through this in a bit more detail, and then we're going to set out a set of rules. Okay. And by the way, the set of rules that we're going to set out are going to be the set of rules that are going to help you do the last part of your homework. So we're getting to the information you need for the last part of your homework assignment. So local independence, every node is conditionally independent of non-descendants given its parents. And let's do a little example. So let's suppose we're thinking about like a course, students in a course, and students might come in with some skills. They may also come in with some diligence or perseverance. I'm going to call this D. And then if you have certain skills, maybe that makes you a good test taker, because you have like test taking skills. Maybe it doesn't take a lot of diligence, but you have you kind of have the knowledge. So okay, that makes you a good test taker. You have some how to. There's also understanding the material. And that does require some skills, but also definitely requires diligence to be able to get through that. And then these things kind of show up in exam grades. And they show up in homework grades. And let's imagine that to do well on the exam, you have to be a good test taker and you have to understand the material. If you understand the material, then you can do well on homeworks. And this is, again, like before we dive into the specific independence relationships, I just want to point out that here's another way in which structured models help you tell a story, where maybe you have some ideas on how things about like skills that people bring to a course or perseverance or diligence that someone brings to a course manifest in what you observe in terms of grades. And then you have the structure that you're going to hypothesize about and do inference in. And in previous cases, when we did like the mixture models, for example, there was no structure, right? There was just a component, or the structure was very simple, right? The structure was just that there's a hidden component, and that hidden component produces all the data that you see. So there's a very flat kind of notion of like hidden or top level variable produces everything at the bottom level. And here there's multiple levels that say that the way in which knowledge that someone brings turns into exam grades, it's mediated through these variables. So then you can start thinking that like maybe if I intervene and just help someone be a good test taker, I don't need to make them a great rock climber, if this is all the skills that someone has. That these are the things that are maybe the places where I could make a difference. All right, so let's do some reasoning on this graph. So given G and U, so these two over here, E, so here's things that we can observe, is independent of the rest of the graph. So it's independent of S, D, and H. Because once you know that someone is a good test taker and they understand the material, then you can see visually how the rest of the graph is blocked off, right, from exam grades over here. So that seems to make sense. Let's try a couple of others. So given S, so you know something about let's assume these are all binary at the moment, that someone has relative skills for the course, are G and U independent? So folks can maybe just put into the chat whether you think the answer is yes or no. I'm seeing a bunch of yeses. And this, again, this makes sense because this is the parent variable. In general, you might think that these two, or in general, these two things might be correlated, being a good test taker and understanding the material, but our graph says that they're correlated because of this thing called skills in our example. And so if we know the skills, then these are just two different children, separate children that are coming off of this parent variable. All right, so that one makes sense. Here's another one. So does conditioning always create independences? So given now E, so you see someone has done well on their exam, are G and U independent? Again, you can just drop in the chat your thoughts. There's a bunch of no's coming up. Great. All right. And what's the reason for that? Well, if someone, let's assume that doing really well on an exam ends up requiring two things. It requires understanding the material and having the right strategy, not getting stuck on a particular problem or something like this. So if that's the case, then if I see a really good exam score, I kind of know that two things had to have happened, right? For the score to be as it is. So in this case, observing something actually correlates two variables that we may have been independent before, but they're not independent now that I've observed something. So hopefully these are kind of intuitive. Or what I'm going to do now is I'm going to formalize these into some rules. So formalize into rules. And these rules are called separation. So again, I think we have I think the intuitions are important. Hopefully we have some of those, and now we're going to actually write out some specific cases. All right, so some node A and some node B are deseparated if every undirected path from A to B is blocked. And how can a path be blocked? Ways to block. So one way a path between A and B can be blocked is that there's some variable A, there's some variable C, there's variable B over here. C is observed. So again, this is maybe intuitive. What's going on here is very similar to us saying that if you observe that this person is a good test taker and that they understand the material, then their exam grades become independent of their skills. So the paths, these are like these ABC type paths over here. Both paths from skills to exam grades have been blocked. And so we have independence between those when we observe G and U. So that's case number one, that if you observe something that comes in between these two variables, then they're independent because this, like C, kind of has the information. Any information about A that would be relevant to predicting B is already captured in C, right? Because the only way that A affects B is through C. Here's and then the opposite case is also true. So this one I think doesn't need much explanation. It's just going in the other direction. And then we have the case where, I want to do this one first. C is kind of in the middle. So you might have a path that looks like this. C is observed, and this corresponds to the case that I asked about where given S are G and U independent. So here's the C, like S corresponds to the C in the middle, and these are the A and the B. We just kind of talk through that. And this is, again, one of these formal rules that once you see the thing that correlates A and B, then any additional, then that contains all the information, right? C contains any information that's relevant, that correlates A and B together. So again, that observing that will result in any additional things about A and B, their variation to be independent of each other. And then the final case is the case that we said was a little weird. So here, if we have A and B both going into C, then A and B are independent. Remember, we're describing situations where A and B are independent. So A and B are independent if C is not observed. So in this case, not observing C blocks the path. And by blocking the path, maintains independence. So it's kind of, there's like kind of double negatives going on here. But if you observe the C, that's this case over here, where given E are G and U independent. And we just argued how that just kind of intuitively didn't make sense. So observing the C would make these A and B's potentially correlated with each other. Whereas not observing the C preserves the independence between them. Because if you don't observe it, then we flip a coin for A, we flip a coin for B. And then once we flip the coins for A and B, we have a generative story that says now we produce the C, the final C in the middle. So if you have an A and a B, you have to check now for any path from A to B. For every path, it needs to be blocked. So again, I'm going up to this simple example. If I said that given only G is E independent of S, then there is one path here that G blocks. So if we are thinking about S as our starting point and E as our ending point, there's one path that's being blocked by G, right? But there's another path that's not being blocked, right? Because a path that looks like this needs to be blocked by observing you, not by not observing you. And since we are only observing G, then this path is not blocked. So it's important to consider all the different paths to be blocked when we're looking at this idea of separation. I'm going to pause there to see if there's any questions about this.
So for the fourth point, A and B, so there's no parents for A and B, right? So if
yeah, I mean, if A and B had some additional parents, so if we have some E going into A and some F going into B, then that would be fine. Also.
So in that case, would A and B be independent given E and F, or?
So right now A and B are independent even without, there's only one path here between A and B.
Mm-hmm.
And if C is not observed, then they stay independent of each other. Let's imagine actually E connected to both A and B and connects to C. So now there's actually two paths between A and B. There's this path over here, and then there's this path over here. So in this case, if C is not observed, then this path is blocked. So we need C to be not observed. But then this one over here with E as the parent looks like case number 3, right? So if we want A and B to be independent of each other, or A and B will be conditionally independent if E is observed and C is not in this particular case.
Sorry, so it's still not clear for me why in some cases we want not to observe something. Can you explain why?
Yeah,
The fourth
so
point is not working.
the idea here is that sometimes an observation correlates things that used to be independent. And I think the easiest example is a case where two things need to be true for some outcome to happen. So in this example over here, for example, we were saying that to get a good score in the exam, you have to be a good test taker and you have to understand the material. Let's say I'm flipping coins and I flip let's ignore the top part. I flip a coin and I flip a coin to say that, okay, you're a good test taker. And then I flip a coin independently. I flip into another coin to say you understand the material. Then if I observe that you did well on the exam, again, if we treat everything as binary, then those two coins, I know that those two coins must have come up heads. But if I didn't observe your exam score, I would be like, I don't know, I guess 50% probability on the good test taker, flip that coin, and flip the understand material coin, 50% probability. But as soon as I observe this thing that can only happen if A takes a certain value and if B takes a specific value, then I know that A and B had to have taken those specific values, and that creates a correlation.
Yeah, thanks. That makes sense. So the sentence you wrote just a tiny bit above, no, on the previous page, just above, yeah. Every node is conditionally independent of non-descendants given parents. Like for the fourth point, I thought that would apply, right? Because there was no parents for A and B.
But these are descendants, right?
So like if we go back then to the fourth point in the next page, aren't A and B like non-parents / descendants?
Okay. Wait, did I have some? Okay, you know what? I'm going to backtrack on this because I think you're right. Is conditionally independent non-descendants. I think we need to include basically the aunts and uncles. David, you're saying it's okay. Why am I confused? Every node.
I think it might be Raphael's confusion about the fourth case on the next page. It's not that A and B have no parents. You're just showing, you're actually not showing the rest of the graph, right? You're thinking about paths between two nodes.
That's right.
But even if the graph was just those three, A, B, C, aren't A and B, like they're not children of each other, right? And
yeah,
so
okay, I'm gonna put an asterisk here. I'm gonna come back to whether we need to think about aunts and uncles, basically, in a more sophisticated way. It's a good point. The rest of this is definitely solid. I feel good about it. So if we have the graph, we have these three cases, we have these cases, we have the deseparation. And then let me think a little bit more carefully about the aunts and uncles case. We'll come back to that. Okay, and that's a good question. All right, so let me just make a quick note about uniqueness. Over here, which is that if we have a causal interpretation, then there is some notion of uniqueness, right? There is a notion of like, if we have something like A to B, then A causes B. But in general, there's a statistical interpretation allows for multiple orderings or graphs. But one may convey the fewest parameters, most independencies. So let me make that a little more specific. So the thing that I'm trying to say here is that when you have a graph, it's just this is a statistical tool, right? It's telling me how to write down that joint probability distribution. So remember that I can always write. So I can always write P of A, B as P of A, P of B given A, P of B, P of A given B, right? This is just like factorizations, conditional probabilities. So, what is special about writing a graph in a particular way? It's about these independence relations, which correspond to parameters, number of parameters. So let us think about that with the graph that we had. So we had the skills, we had the diligence, we had the good test taker. Other way. And understanding the material. We had the exam scores, and we had the homework scores. And this is what our graph looked like. So let's count the number of parameters needed if we assume that all nodes are binary over here. So for S, we need one parameter. It's a single coin flip, right? To skills or not skills, of grossly simplification of like what happens in real life. D also is a coin flip, right? And then G, well, G has to have I have to have two coins available. I have to have a coin available for if S comes up heads, and I have to have another coin available if S comes up tails, right? So we have two possible situations, and so we need two parameters. We need a coin for basically the two different situations that S creates. We have U, and U actually has 4 situations that can possibly occur. So U needs a separate coin or a separate parameter for each setting of S and D. And so that's 4 over here. By similar argument, E also has 4 different parameters that are needed, right? It needs a single parameter for all 4 settings of the potential parents. And H needs 2 over here. So total over here is 14 parameters that we'd have to learn, right? If we're learning this, we had a data set, then let's see, there's a question, if you know S is true, then automatically know it's not false. Right, so if you know that S is true, so there's going to be like a probability that S is true here. And then for G, we're going to need a probability that G is true given S is true, D is true. That's like parameter 1. Then we're going to need a parameter for P, G is true given S. I'm going to start using zeros and ones here for all the different cases over here. Oh, but D doesn't affect. Oh, did I do it backwards? Okay, I did it backwards. Okay, thank you for catching that. All right, so where am I? Okay, so I need D is 1, S is 1, G is the one that, wait, G is 2, right? That was fine. U is the one that needs 4. Sorry, I was explaining the wrong piece here. I'm a little out of sorts today, aren't I? Okay. So G is going to have 2 settings, and U is going to have 4 settings. That's correct. And and those different settings are coming from the fact, are coming from the U given S equals 0, D equals 0, U given S equals 0, D equals 1, U equals S equals 1, D equals 0, U equals S equals 1, D equals 1, right? So those are 4 settings that we have for the parents. And for each of those, we're going to need to know what's the probability that U comes up heads. I think we're good here now, right? So we get 14 parameters in this particular way. But I could have drawn this graph differently. So what if I drew the graph differently? This is the point I want to make about uniqueness. So this graph over here kind of insists on a generative story that starts with S and D, and then goes to G and U, and then to E and H. So if I was sampling, for example, if I want to generate a potential vector out of this data set, then I would start by generating S and D, then I would sample G and U, then I would sample E and H, right? But potentially I could draw the graph differently. And I could say, well, I insist on drawing E first, right? Because I want to do that. I want to sample E first. So if I sample E first, and then I insist that I want to sample H second. Let me move this up so we can see both at the same time. I'm going to insist on sampling H second. Well, I'm going to need an edge from E to H, because in this graph over here, there is a relationship between E and H. So the next thing I decide is that I want to sample U, right? As I'm arbitrarily now choosing my sampling order, and I'm asking, how simple can I make this process? Like, what are the minimal set of connections that I need if I arbitrarily choose my own sampling order rather than the sampling order that is suggested by this particular generative story, this particular graph? So if I have U over here, well, U is going to depend on both E and H. So I need to draw arrows coming in like so. Let me now go on. I'm going to say, well, now I want to sample S. Well, to sample S, let me see, where do I want to put it? I'll put it over here. To sample S, well, if I have available to me U and I have available to me E, then I don't need H, right? So if I need to sample S, I know that S is going to be independent of H given the U. But it's not going to be independent of E because I don't have G available to me yet. So I get this particular graph over here. And now let's keep going to add in, let's add in G. I'm kind of going in an arbitrary order here, not necessarily a smart order. So now if I want to sample G, well, I'm going to need to know what S was to produce the G. I'm also going to need to know what the E was. And if I know the E and the S, then I can sample G without needing to know anything else about the graph. And finally, we get to D over here. And to be able to sample D, I'm going to need to know the U, and I'm going to need to know the S. So what I've done here is I've made a graph. So this is a graph with a different, so this is a graph with a different topological ordering. It's one that I chose arbitrarily. It's not necessarily a smart ordering. It's just a different ordering, right? And what I want to point out here is that it's a graph with a different topological ordering and a minimal number of connections given that ordering. So suppose that this ordering is kind of the minimal ordering. Minimal ordering kind of has the most independencies in there, right? What happens if I try to take this graph and I impose a different ordering, a different sorting on the variables? Well, I get something that is a lot messier over here because as I was talking through each of these pieces, for example, when I got to U and I had E and H available, I was like, okay, then U needs to have both E and H as parents. Where I got to G, and then G needed to have S and E as parents. So there's a lot more nodes here that have more parents compared to the case before. And in fact, if I count parameters in the same way as above, I'll get 19 parameters. So, which is more than the 14. So what this is saying is that if you choose, if you choose the wrong ordering, then your graph is going to end up having to be more complicated, right? That there's certain minimal dependencies that to be able to encode the relationships that are in the graph, in some senses, you're encoding extra, right? You have to learn more parameters rather than if you had the encoding right, the sort right. So if you had the ordering of the variables correct from the beginning and you knew that S and D were at the top, then you could make this smaller graph. But if you didn't know that and you tried to force a different ordering, you'd get something else. So I'm pointing this out as largely as an exercise of, partly there's inefficiencies potentially if you do the wrong ordering, but also to point out that it's not that you can't do it, right? Because again, these graphs are not saying anything about causality, unless I specifically say that I'm working with, causal interpretation. Usually Bayes nets, the basic version of Bayes nets are just ways to simplify how we look at distributions. And so I can always rework the way that I do my conditional independencies and the topological sort, the ordering in which I condition. And certain choices of how I do that conditioning might result in more minimal representations than others, right? That's the key point. Another way to point this out could be that I'm assuming that this is P of S, P of D, P of, let me write, P of D given S, P of G given S, D, P of U given G, S, D, P of E given S, D, G, U, P of H given everybody else, right? So if I chose this ordering to write out my conditionals, then I can start simplifying. I can see that guy goes away. This guy goes away. When I'm doing U, G goes away. When I'm sampling from E, then my S and my D go away, right? So I wrote down a particular ordering in which I wanted to write down my conditionals, and this graph told me that I can get rid of a bunch of variables. I can make things a lot smaller. But if I had insisted that I wanted to instead write this as P of E, P of H given E, P of U given EH, etc., that's allowed, right? That's absolutely, because I can choose to do my conditionals in any order that I want. But what I'm noticing is that I choose to do my conditionals in a non-ideal order, then I can end up needing more parameters. And this is going to be important next time on Thursday when we have to do inference as well, right? Choosing kind of orderings of conditionals ends up being important. But okay. Last thing that I want to do before we go into a concept exercise is just make some final notes on other graphical models. So we've focused on Bayesian networks and specifically on directed acyclic graphs for today. And these are, I find DAGs to just be very intuitive. I really like them. And they extend in really nice ways. Like as you add more variables, it's just like adding more conditionals, right? You can just hang in that next variable off of the rest of the graph. They marginalize easily, they extend easily. Some of my past research has been with models with infinite numbers of parameters, and in that case, certainly having models that can grow and shrink and kind of handle large things is really important, especially when it becomes countably finite and infinite. So that's all. They have some really nice properties, but there are other versions out there as well. So the two other types of models that you might see, just so you've seen them here, are undirected graphical models. And these look like something like this. And they also imply a particular factorization. So here, P of A, B, C, D will factorize as some potential function phi of A, B, and C, because that they form a group, a clique, times a potential function of C and D. And the tricky part here is that how do you normalize? Right, so this is written down as potential functions, but we have to somehow make sure that all the probabilities end up summing to 1. And with the Bayes nets, this was easy because each of these arrows were conditional distributions given their parents. When you have just some sort of arbitrary distribution here as phi, then that becomes a little more difficult. You know, how do you normalize? But these are popular models, and definitely in image segmentation and such. These sorts of models have been used a lot as graphs over pixels in an image and these sorts of things. And the other main kind are factor graphs. And in factor graphs, we explicitly note down where things interact. So we could have something like A, B, and C interact through this factor over here. Maybe B and C have another factor that they interact through. And then C interacts with D through another factor. So this says that P of A, B, C, D is equal to some phi of A, B, C, some phi of B, C, phi of C, D. And the nice thing here is that over here, we couldn't say that there's an additional relationship between B and C, right? Once we made the triangle was made. Or we also couldn't distinguish, for example, between something like this. And maybe there's just pairwise relationships between A, B, and let me actually draw that one. That's a good one to include. So suppose that I was in a situation that looked like this. So I have a triangle here, A to B, B to C, C to A. But because of the factor graph notation, I can write this as A, C, A, B, like this. So I know that there's some smaller potentials, but still the same issue of normalization comes into play. So there's other things that these things can be useful. Factor graphs are a very expressive way of describing relationships between different variables, and there's things that undirected graphs can do that directed ones can't, and vice versa. But for now, we don't really have time to go into all details for these. This could be, and you can have entire courses on graphical models. And for now, we're just going to focus on the Bayes nets, which have some really nice properties and cover a lot of, provide a way for us to think about a lot of the models that we've already seen in class.
So sorry, just for undirected graphical models, you factored by maximal clicks, or?
So right, for undirected graphical models, the clique describes what the potential is. Yeah,
Okay, thanks.
Yeah, that's the convention. The black boxes are describing basically each black box corresponds to one of these keys over here. So it's being more explicit about how variables relate to each other, because in the undirected case there was just this this triangle, and so we had to have this full factor over here. In the factor graph case, we say that there's a difference between something that looks like a triangle. Let me draw the other version in red. There's a difference between this red picture and this black picture over here. All right, cool. So in that case, I'm going to stop my share, and we're going to go on to a concept check where we'll do some parameter counting. Let me just pull that up and share. So here is the link to the concept check. Share here. So here's our concept check. We have a setting with 5 different variables. So here's the shape of the graph. The shape of the graph is always going to stay the same in this exercise. But we're going to consider 3 possible instantiations. Remember from the beginning, we said that this describes the structure, but doesn't describe what the variables are, what the relationships specifically are, you know, the Gaussians, the whatevers. So the first case we're going to consider is all of these variables are discrete scalars that can take on 4 values. So think of these are all, each one of this is a 4-sided dice, right? Now, the second case is that all variables are scalars, one-dimensional continuous scalars with linear relationships. So b is equal to some linear function is equal to some linear function of a plus some noise, no bias term. Case 3 is that all variables are 4-dimensional continuous vectors, and the relationships again are linear. Okay. So for each of these cases, what we'd like you to do for case 1, 2, and 3 is determine how many parameters are in the model, ignoring A, because A is kind of, I just don't want to deal with like the number of parameters in the initial Gaussian or whatever it is that creates the continuous things. But things aside from A, how many parameters are there? Don't worry about the noise also. Let's suppose that the noise is fixed, noise is given. And then consider why can a continuous model potentially have fewer models. So I guess parameters. I guess we've given away the continuous models to have less parameters than the discrete ones. But why might that be the case? So folks can go now to your rooms. And
let me go ahead and do that quickly.
Okay. Oh, cool. Okay, thanks.
Yep.
I'll come back.
Oh, good, and you made it back. Okay. I cleared up the confusion finale. I typed it into the Google Doc. Actually, what you wrote is completely fine. It's just that the definition requires the local independence definition requires that there be no information about the descendants. That's part of the definition. You insist in defining local independence that that we have no information on a child. You're on mute. You're on mute. You're on mute.
I think she might be frozen for me. Oh, no, never mind.
No, I think maybe her loudspeaker, either she doesn't hear us or let's see.
Oh, and I'm muted. Okay, that was
there you go.
not useful on both ends. I can't hear you either.
Good. Okay. Sorry. So your definition was fine. The important thing is.
Can you hear me?
Yeah.
You can hear me. I cannot hear you.
Oh, you still can't hear us. Okay. Weird. Yeah, we hear you fine.
That's strange.
And Lucy can hear
I can
me.
hear you, but I cannot.
Wow.
I have no idea what's going on here.
I think it's Finale's speaker that's not working.
Lucy, can you say something?
Hello.
I can hear Lucy.
It's very strange. Okay.
Yeah.
Why is my speaker so?
Wait, she said she could hear me.
No, she said she couldn't hear Lucy.
Oh, I see. You can hear me. Okay.
Okay, now I think it's back. I have no idea what just happened there. I just
Okay.
reset the sound setting. Okay. Went into audio settings. That is okay. That's the first time that's ever happened. I was saying that I'm just looking at the part where I slightly tripped up.
Yeah, and I posted on it in the Google Doc, and
Okay.
your definition is basically fine, but it's just the definition of local semantics requires that we don't have any information on the descendants.
Yeah, that's what I said while
Right.
I was.
And you wrote the word only,
Yeah.
but you just didn't emphasize it. So that clears it up, because he was talking about this example. So
Right.
pretend those are the only ones. Then these two, trivially, we know their parents. But the point is, we know about their child now. So that's precluded by the local semantics definition.
Yeah. Okay, that's cool. Okay, yeah, we're definitely on the same page.
Maybe you can cycle back when we get them back. And
yeah.
I always trip up over that as well. And also the whole deseparation thing, there are all these there are double negatives that flow in two directions.
Yes.
And Lucy says record is still on. Okay, that's too bad.
Oh well, that's fine. They can they can see me futz with audio. I'm okay with that. Okay, let's close all rooms and bring folks back. All right. Cool. All right, so we're getting some responses in, which is great. So let's just go through these cases in terms of just how we would do them, and then I think that's probably the most efficient way. So in the case that we have discrete variables, what we're going to end up with is we will need 3 parameters for every case or every setting. So for example, for variable b, we're going to need, sorry, I'm going to switch back to my whiteboard. For variable b, for variable b, there's 4 settings of a, and for each of those 4 settings of a, I'm going to need 3 parameters, right? Because the last one is just summing to 1. Same goes for c and e, right? Each of those only have 1 parent. But for d, we're going to have 16 settings, potential settings, and 3 parameters for each of those 16 settings. So these are E, C, and B each have 12 times 3. For the 3 of these, this gives us 36. This gives us 48. That gives us 84, which was the largest number that we had in the solutions. And then in the two other cases, and I realize we're a little over time, but I'm just going to go through the other two cases pretty quickly. So this was the discrete 4 values case. So now let's go through the continuous 1 value or 1-dimensional case. So in this case, A, B, and so actually E, B, C, these are all going to be the same again. They only need 1 parameter because they only have 1 parent. D is going to need 2 parameters because it has 2 parents. It's all linear, right? So it's just a coefficient on B and a coefficient on C. We end up with 5. And there's a question about where, what about A? So the problems that ignore A, the problem statements that just ignore the number of parameters in A. So I'm ignoring that. And where did the 3s come from up here? The 3s came from, so these are the settings of the parents. So these are the number of parent settings. And then these 3s over here are coming from number of parameters needed to describe a distribution on 4 discrete outcomes. So to describe a distribution on a 4-sided die, we need 3 parameters because the 4th parameter is just 1 minus the sum of the first 3. And this last 3 over here comes from the fact that E, C, and B are the same. So I'm just multiplying by 3 for each one of those 3. Great. All right, so then if we have 4 values, continuous, over here, we have B, C, and E, again, are going to be analogous. They each are going to need 16. We're going to need a matrix now to take a 4-dimensional A, for example, and turn it into a 4-dimensional B. So there's going to be 16 in each one times 3. That's going to give us 48 for those. But D is not going to be too bad because D has now 8 parents, right? That need to be turned into 4 values for 4 dimensions. For D, gives us 32. We put those together, we get 80. Right. And so we end up with less parameters in the both continuous cases, right? If you make this 4 continuous values, it's less. If you have it be scalars, so discrete scalar versus constant scalar, it ends up being less. Why is it less? Are continuous numbers somehow easier to deal with? No, it's less because these are linear. Linearity is a big assumption. Okay. So that's the key point here is that, things, this discrete thing is describing every way of creating that discrete distribution. Whereas if we make this linearity assumption, we're making some really specific assumptions here. We could have had like a deep network containing A and B, and suddenly there would have been a zillion parameters. Cool. So that's going through the concept check. And then the very last thing I'll note is that bit of confusion about the independencies and the non-descendants. I just want to emphasize that the statement that I was making about every node is conditionally independent of non-descendants given parents is only if the children are not observed, right? So that's kind of what was implicit there. So just wanted to clarify that part as well. So now everything is consistent. Great. So I'm going to stop the recording, and anyone who has any remaining questions, I have a few minutes I could take.